Hello together. We just defined the adjoint. The defining property is still shown here in the yellow box. So this has to do with a boundary linear transformation between two Hilbert spaces. Given that thing, call it T, then there is a unique object T star, which boundary linear transformation going the other way, and that satisfies this property in the yellow box. We proved it through an explicit construction. It uses input from the Riesz representation theorem as well as the dual transformation that we defined and studied, I would say, extensively in chapter 3, in the Banach space chapter. After defining it, then we showed that that yellow box defines it uniquely, and now we are here. We want to check a few of its properties. There are 6 properties, and well, it will take a while to prove all of them. We will not go in the order written. It's easier if you jump a little bit around. So we begin with 3. 3 is the one that if the starting linear transformation is invertible, then the adjoint also has to be invertible, and there's a pretty formula. So begin with 3 and compute for any x in H1, y in H2. I mean, proving those properties is not super hard. Actually, it's not 3 that I begin with. This is property 4. The property 4 is the property that if you compute the adjoint of the adjoint, then you go back to the map itself. Okay, so let's do this. Let's have adjoint here, x, y, 2. Well, then what you can do is you can use the property of the inner product that allows you to swap the order of the entries at the cost of having a complex conjugate bar here. And now you use the yellow box. Maybe I will just indicate it like this. The yellow box said you can move this guy here to the first entry and you get rid of 1 star there. So this will be T star yx, but now you're in the first space. The complex conjugate just stays as is. And now you can undo the order shift here, just get rid of the complex conjugate bar, and now you use the yellow box again. Right, so now you move this fella to the first, so that will give you tx comma y, right? And this is again in the second space. And since this holds true for all x and y, you have equality between the green underlined thing, and that of course implies that T is equal to the adjoint of the adjoint. Okay. These are standard properties of the inner product that you exploit now to conclude this. So T star T is equal to T. Okay, good. Now, moving to 1, we use that, we will use the explicit formula that we have, right? So we use that Ci is conjugate linear. This was the one that assigns to a vector that linear functional where the vector itself appears in the second entry. So we use that this one is conjugate linear. And the dual transformation from the dual Hilbert spaces in this order linear. So that map that assigns T to its adjoint is conjugate linear by definition, right? Remember, maybe I'll write this here. So T star, how was it defined? It was in the order C1 minus 1 T dual transformation and then C2, right? So that as a composition of conjugate linear maps is conjugate linear. Okay, that's clear. Let's write out the conjugate linearity once. Alpha T1 plus beta T2 star Well, if it were linear, then there would just be alpha t1 star plus beta t2 star, but since it is conjugate linear, I mentioned it before, you have to give the complex conjugate bars here on top. Of course, if the underlying scalar field is the real number field, then there's no need for those bars, but in the complex number field there is. Okay, for any tj in L h1 to h2. Okay, and alpha beta scalar. All right. Moreover, so that first property was conjugate linear isometric isomorphism. So we got conjugate linear. Now we have to show maybe isometry. Moreover, since the CJs are isometries, and since, well, the dual transformation is an isometry, well, we conclude at once that the operator norm of the adjoint is the same as the operator norm of T itself. Okay, this should be clear. Why is this? Because up here in yellow there's still the formula. So if you look at T star, let's think. So T star goes from H2 to H1. So if I look at an X here, and then I look at the norm, that will be a norm in the first Hilbert space. So by definition, this is C1 minus 1 dual C2X in the first space. And now what you do is, well, you group these two guys together. Okay, I should do the grouping slightly different. Idea is correct, but execution faulty. So you group like this, okay, and now you use that C1 is an isometry and hence its inverse is also an isometry, right? So this will be equal to, because C1 is an isometry, T2, C2X. Now this will be an operator norm because the dual transformation it maps well to the dual space. Okay, so now you continue with the grouping. So you can group here, for instance, next, right? And yes, that you can do. Or you can at this point already optimize over the x to get the inequality, right? I mean, what you can do is you can prove it that this is good, and at this point what you can do is you could bound this by, well, T transposed the C2 of x, for instance. Then you can optimize. Then you would here use in the second case that this is this one, C2 of x. Then you optimize, you get the inequality that the operator norm of the adjoint cannot exceed the operator norm of T, and then you can reverse this logic, right? So this using the other part of the proof that we're going to do now, this guy is invertible, right? And then you can just swap it around. Okay. So that works nicely. So you have this. It's an isometry and thus injective. Good. Include that this holds true. It has the map T to the adjoint is an isometry and thus injective. Now, why is it surjective? Well, that's because we started with proving the fourth property, namely T star T is equal to T. That simply says that map is also surjective, right? Because every bounded linear transformation is the adjoint of something, namely its own adjoint, right? So that's what it says. So that's surjectivity. So altogether, that map T going to the adjoint is invertible by the inverse mapping theorem, Right? The inverse mapping theorem comes handy because it just needs that you have a bijection between Banach spaces, and here we're working with Hilbert spaces, so that immediately then tells you that the inverse is bounded, and hence that map itself is invertible. Okay, good. This yields 1 by the inverse mapping theorem, so we have established 1. Good. Now what comes next? Property 2. Property 2, this discomposition property. Moving ahead. Property 2 is also immediate. Is immediate since okay, yeah. Well, it's again, you have to play around with the yellow box. 1, same trickery. First you exchange the orders. That the exchange of orders I do because in my yellow box the start quantity always appeared on the right rather than on the left. That's why I do it. So now you use the yellow box for the first time. You can move the T star over there and get rid of the star by doing that. So Ty S star X. Now this is in the second space. The bar stays. Now you use the box again. Move this guy over. And you have S, T, Y, X. Now you're back to the first space. There's a bar. Oh, not the first space. Yeah, this T goes from first space to second space, and S goes from second to third, right? So there's a third space. Sorry. Third space. And now you swap X, T, Y. Third space. Well, and now you use the fourth property that we already proved. So the fourth property is X, oh yeah, lots of brackets, lots of stars, S, T, star, star, right? Because the adjoint of the adjoint of the adjoint of the adjoint transformation is the original transformation. So then you have this, okay? And this holds true for all x in H3, y in H1, and thus by uniqueness of the adjoint well, you just have to read this here equal to this, okay? So that tells you that the adjoint of ST is, well, T adjoint S adjoint. So we have the adjoint of ST is T adjoint S adjoint. Excellent. Good. Now we will prove that statement about if the original transformation is invertible, then so is the adjoint, and there's this formula. Then we still need to do number 5 and number 6. Okay. All right, furthermore, given invertible T, so T minus 1 T, since these are linear transformation, not necessarily operators, you have this equation, and if you compose the other way around, you get the identity on the other space, so on IH2. So given this and this, we use that, well, T star, so remember T star, so that formula again that constructed it explicitly, this was C1 minus 1, T dual of it, and then C2. So if T is invertible, then one of the exercises showed that the dual transformation is invertible, and C1 and C2 are already invertible. So that means that the adjoint as a composition of invertible linear transformations is invertible. Okay, so that we get for free since we know something about the dual transformation. And the invertibility of those C's comes from Riesz representation. Okay, we use that this is invertible, and moreover, how does the equality follow? Well, let's look at T star. t minus 1 star. By the second property, why is this the second property? Oh yeah, this is that S and T, the dual, not the dual, the adjoint thereof you can compute by swapping the orders and those individual adjoints. So you get t minus 1 t star, right? So if I put the star outside over both, I have to flip the order, and that's precisely what happened here. Here on the left, there's t on the left and the inverse on the right. Here with the star outside, it's precisely the other way around. And then t minus 1 t is the identity on H1, okay? So now you have the identity on H1, but you can clearly convince yourself by looking at that yellow box that the adjoint of the identity is the identity itself. Okay, so there's no surprise here. And similar thing happens for t minus 1 star, t star. Again, you use that property, so t minus 1 star. This is the adjoint of the identity on the second space, which is just the identity itself. All right, good. And this proves, which proves the identity. All right, so I've checked that t minus 1 star here is a two-sided inverse. That's precisely what these two equations up there tell me. And since it is a two-sided inverse for what? Well, precisely for the adjoint. And since inverses are unique, that tells me immediately that the adjoint of t minus 1 is the inverse of the adjoint. Okay, that's the logic. Okay, good, because inverses are unique. All right, so now we have 1, 2, 3, 4. Now comes the statement about the topologies. And I said this is sort of fancy talk about simple statements, about convergence of sequences of bounded linear transformations. And then what can I say from that convergence statement for the corresponding convergence of the sequence for the adjoint operators. Okay, so next we pick a sequence, Tn, bounded linear transformation from H1 and H2, so that Tn to T in L1, L2 as n tends to infinity weakly and uniformly. All right, then I will show that the same convergence holds true, the same weak and uniform convergence holds true for the adjoint sequences, right? So the sequence formed out of the adjoint operators of the T, N's, and T. All right, so but this is easy. So look at this guy here to establish uniform convergence. So we already checked that the mapping that sends T to its adjoint is conjugate linear. So this statement here is certainly true. That uses the linearity, the conjugate linearity. And then if you remember, that first property also said it's a conjugate linear isometry, and that statement simply means that the operator norm of the adjoint is the same as the operator norm of the original transformation. So that's what you use here. So you get rid of the star. This is property 1. This is also property 1. Yeah, but if this converges uniformly, then this goes to 0, right? As n goes to infinity. So you have that the sequence formed out of the adjoints also converges uniformly, right? And that's what we mean, that that map that sends T to the adjoint is continuous in the uniform operator topology. Okay. Now, same thing for the weak convergence. So let's look at Fn T star of x. Now, since we're here in a Hilbert space, we know exactly how every linear functional looks like. This is just inner product with something. So here this will be of the form Tn star x, and then here's again this unique vector y. This will be in the first space. Now you can use the yellow box again. You move this guy over there, so you get x. So right, so the first one, this is Riesz representation. And now we have it over here, Tn yf, okay. Now this is equal to Tn y, oh, f, y sub f x. This is in the second space. Oh yeah, here I forgot the indices. This is in the second space, and then here we have a complex conjugate bar on top. And this one here, how can you view this? Well, you can write it as a g sub x evaluated on Tny, and then complex conjugate bar. So what is the g sub x? Well, probably can guess. So gx of y is simply linear functional. That is this inner product, right? This is a bounded linear functional. Okay. Yeah, but you have weak convergence, right? So you know precisely what the image sequence T and Y does when evaluated on any bounded linear functional, right? It converges, right? So this will go to gx ty. This is weak convergence of the sequence of bounded linear transformations. Yeah, and now you just trace back how all these things were defined. So you have, right, so here's this y sub f. I keep forgetting the subscript f. So you have t y f, comma x. This is in the second space. You flip the order around t y f, second space, and now you use the yellow box again. And you get t star x y f in the first space, and then you use again Riesz representation theorem. This is precisely f t star x, and there you have it. This here, as n goes to infinity, converges to this, right? And that means the weak convergence is lifted to the corresponding sequence of adjoint linear transformations. Okay, this holds true here for all f in H1. Good. So in turn, let's write it in words. In turn, Tn star goes to T star weakly as n tends to infinity. Okay, we will discuss the, I said in the formulation of the theorem that this is in general not true when you look at strong convergence, and we will do this with an example once this theorem is proven. Okay, so instead we will now prove 6. That's the last one. Moving to 6, we know, because operator norms are submultiplicative, so you have t star t. Remember, submultiplicative was the statement about st. Operator norm thereof is at most product of the individual operator norms. So use this here. You have t star t, then you use property number 1. Property number 1 said that the map that sends t to the adjoint is an isometry in particular. That means the operator norm of the adjoint is the same as the operator norm of t. So what you generate here on the right is just the operator norm of t twice. So that's why there's a square. Okay, and well, you can do the same thing, of course, the other way around. Gives you the exact same result by the same argument. Right, this is by 1. This one here, okay? But also, now how do we get equality? Well, look at this one here. So remember the operator norm, this is tx. Now t here maps from the first space into the second, so there's a subscript 2. Here will be a square. Then you optimize, say, over the sphere in the 1 space. That is equal to, just use the definition, x 1 1, these are inner products, txx 2. Now you use the yellow box. I have to write it on the next page. You move that 1 t to the other side, so you have supremum x 1 1 x t star tx 1. Now you can use Cauchy-Schwarz inequality. This was material in the first chapter. x1 t star tx 1. Yeah, and then, well, you use that standard trickery again, that this is t star t x 1. Okay, and then you have the x1, the x in the norm on the first space squared. You optimize it over the sphere, so that optimum there is 1. So what you get there is at most t star t. Okay, and that is the reversed inequality, right? So together we have just shown that the square of the operator norm of t is at most the operator norm of t star t. Okay, so we have shown that t star t is equal to t star. How do you get it the other way around? Well, since this equality holds for all t L1 H1 H2, it holds in particular for the adjoint itself, right? For t star from H2 to H1, right? So you replace now in that green underlined thing every appearance of t by t star. So you have this. Now on the right, this gives you immediately by property 1, because that map is an isometry, gives you this. And here by property 4 you get just a t, right? And that's the equation the other way around. Okay, this completes the proof of this theorem, which was rather long. Okay, all right, I will see you in the next video.